Hello, this is Daryl Korn, and I'm going to walk through homework 6 for Intro to ML. Let's start by looking at the code. So my code here, I was able to keep it all into one script, fortunately. Problem 1 asks us to display some PCA and t-SNE visualizations, which you can see right there. Problem 2 asks us to use the elbow method to find optimal K, which is that plot, and display some silhouette plots of the found optimal clusters right there. And then we use that silhouette plot to pull out some core and border samples for each class. So we have that for a little bit. Then problem 3 asks us to go back, and now we're finding optimal K through a transformed 20-dimensional data set. So elbow method there, along with the silhouette coefficient. And then problem 4 asks us to calculate the adjusted RAND score for either of the models we've trained. Lastly, we have the extra credit illustrations. Okay, let's get into the analysis. So problem 1. This is just about visualization purposes. So we want to scale the data to be within -1 and 1 for both the PCA and the t-SNE. And this is mapping 128 dimensions down to only 2 so that we can display it on a scatter plot. I want to point out that within the PCA, when we take 128 dimensions and put it down to 2, we're only accounting for about 17.94% of the explainable variance. So it's not a whole lot. We wouldn't want to use this for a whole lot of analysis purposes, but it is good just for visualization. And we can tell from this PCA visualization, figure 2.1, that we're seeing some classes that might be kind of similar because they're overlapping quite a bit. These purple and yellow classes, which I believe are the plane and ship classes, those seem to be very on top of each other and could be related, as well as these two green classes here, which I believe are the horse and bird classes. They're also overlapping. The car class, the blue one, that seems to be quite distinct. Now, if we look at the t-SNE visualization, figure 2.2, we have a lot less overlapping. So t-SNE is able to kind of separate out these classes just a bit more and show that maybe there is more of a distinction between them than what PCA let on. We can see that the purple and yellow classes are no longer on top of each other, as well as the two green classes are a bit more separated out. But one reason you might want to use PCA instead of t-SNE is that maybe these overlapping instances are telling, and you might want to use that going forward, in which case PCA would be better. But if you know the distinct t-SNE is probably a better visualization of the data. On to problem 2. So we're looking for optimal K for a K-means clustering within the 128 dimension scaled data. And I found using this elbow method here that the optimal K was around K equals 5, because that's where this point is kind of closest to this bottom left corner. And that also makes sense because there's 5 classes in the true labeling as well. So we kind of have the foresight of that as well. Moving on to the silhouette coefficient, though, when we use K equals 5 and we get our, our clusters, we can see that clusters 4 and 5 down here, there's a lot of these negative values, which are indicating that a lot of samples in these clusters are a lot closer to other clusters than they are to the core region in their own cluster. So that's saying that maybe it's not the best, we might not have the best clustering algorithm going on here. And that's further supported by this average silhouette coefficient, this red line here. We can see that it's not quite at 0.05, which is not very high. So that's something to take into consideration going forward. Okay, problem 2, we also want to use the silhouette coefficient to identify core samples and border samples. core samples are going to have a absolute value coefficient, silhouette coefficient close to 1. Oh, sorry. They're going to have a value close to 1. A value close to -1 would be a very poor core sample. So the silhouette coefficient, these are going to be I've selected for the maximum silhouette coefficients in each of the classes. And so you get these 5 images, one per class. And one thing to know about or notice about them is that they all have very nice silhouettes, really. They're very clearly each of their own classes. Whereas the border samples, these are going to be silhouette coefficients closer to 0, where they're kind of on the edge of their clusters and are getting to be closer to other known core samples. And you can see why the k-means clustering model is a bit less sure of these, especially this boat in the bottom right corner. It doesn't really look like much of anything. And the plane there is also not very distinct either. So that is useful to know for some of these samples. On to problem 3. So problem 3 is, instead of doing a clustering algorithm, or creating a clustering model on the 128 dimensional data, we use PCA to reduce it down to 20 dimensions and then train a clustering algorithm on that instead. Oh no, go away. Not now. So again, we went to scale our data between -1 and 1. And we then, after we reduce our dimensions down to 20, I wanted to state that now we are explaining about 50.31% of the variance. Before, when we just went to 2, it was 17 something. So 50 is much better. Still could be better, but it's better than 17. And here I also found that the optimal k is still at k equals 5. But training a k-means algorithm on this and then plotting the silhouette coefficients, we can see that we have a much better looking silhouette plot, not nearly as many negatives, and our average silhouette coefficient is much higher. It's now solidly above 0.1. Okay, problem 4 is looking at the adjusted RAND indexes of our 2 models that we've trained. And I found that I got the same ARI score for both models, interestingly. So the 128 dim and the 20 dimension data, they both got 0.69 as their ARI score. Sorry. So I think this must be saying that these 2 k-means models must be finding very similar patterns within the data sets. And I also created a random data set and tried the ARI score on that just to show that that's sort of the baseline of just a 0 if it was truly random. So I think these models are finding similar patterns. Okay, to conclude this homework, I believe that the transformed 20-dimensional data has the better ability to generalize to new data. Although both models had the same ARI score, I think using the silhouette charts, we can see that the 20-dimensional data, each of the samples there are located much more closely to their core regions rather than to other regions or to border regions. Also, just by going off Occam's razor, I think it's better to pass a 20-dimensional data set to a predictive model rather than 128 dimensions. So also, this is kind of getting into the extra credit bit, but the 20-dimensional data, I thought it was able to have, when I visualized it using t-SNE, I was able to pick out more separable classes rather than when we visualized the the full data set earlier in the presentation. So I also wanted to take a crack at the extra credit for this homework. So for each of these displays here on the right, the colors are the true labels and the different shapes are the predicted labels. And it's kind of hard to pick stuff out, but I think to compare these two visualizations, I think TSNE still shows a better linear separation between the classes, especially between the car and ship classes, or sorry, especially between the ship and plane classes. Now the ship is purple and the plane is blue. And so here in 7.1, we can see that these are right on top of each other through PCA. But if you use TSNE, they are actually very quite distinct classes. Um, Similarly, between the car and ship, which car is um, red. The car is quite distinct here in PCA, but it's even more distinct, I think, in 7.2 through the TSNE. And another thing I wanted to comment on that I noticed about these algorithms is that the PCA display seems to favor homogeneous circular shapes. So we get these circular clusters that are all pretty much the same size in these visualizations, whereas this T-SNE is a bit okay making these irregular shapes, which you can definitely see in the bird or yellow class here, which is this lumpy sort of shape. So that, I believe, concludes homework 6. Thank you for listening.